So in this video, we're going to talk about a fairly important topic when it comes to talking about acid-base neutralization, and that is the subject of pH curves. All right. So if you've got a situation where you've got an acid and you're adding and you're neutralizing it with a base, all right. One thing that you should realize is that even though we're eventually going to neutralize the reaction is not going to get neutralized immediately. All right, like just for example, if we started this neutralization and we just added one little drop of our base, all right, hopefully you'd realize, well, that's not going to be enough of that base to fully neutralize the acid down here. All right, we need to add enough of this base so that for whatever reaction you're doing, for every 1 mole of your acid, you've added 1 mole of your base. All right. So the thing is, as we are adding our acid or our base here, and in this example, we're going to be adding a base to an acid. Hopefully, you realize that you're gradually going to be getting an increase in the pH here. All right. In the beginning, it's 100% acid. All right. And in the end, it's going to be mostly base. All right. And so over time, you're going to see the pH go up. But the way that the pH goes up is going to be different depending on whether these things are strong acids, strong bases, weak acids, or weak bases. All right. So the first case that we're going to do is evaluate what happens when you add a strong base to a strong acid. All right. Another way that we could say that is that we're titrating a strong acid with a strong base. All right. So we're titrating this thing down here with the material up here. All right, and generally this is done where this material right here is in a burette, and so that you can measure the volume that you're adding. And this is the way that it's going to look. All right, and one way to help remember this is just to realize in the beginning it's 100% acid, so we are 100% strong acid, so we would expect a very low pH. If we were to add a whopping amount of this strong base, eventually this is going to become more like the pure strong base, so that's going to have a very high pH. But the important thing to remember is for a period of time, as you're adding drops here, the pH stays very low. All right, but then you get this very sharp increase. All right, so one feature of this graph that is very important is this point right in the middle, which is called the equivalence point. All right, so from a graphical point of view, all right, what is the equivalence point? All right, not talking about the chemistry, but just in terms of what this curve looks like. The equivalence point is going to be what's considered the inflection point. All right, and that's when essentially you can see here this is concave in this direction, and up here this is concave in this direction. So there's a point in the middle of this line right here where it goes from being concave, curve goes in one way, to the curve starting to go the other. That's the inflection point. All right, and that's what is going to be what's considered the equivalence point. And there's something that's important about that chemically. That's going to be the point where the number of moles of the base added is equal to the original the number of moles of the original acid in the solution. All right, so that's going to be the point where you've added just as many moles of this stuff as there were moles in this stuff to begin with. All right, and if this is a strong base with a strong acid, if you were to say what's the pH at that point, it would be a pH of 7. All right, so we could do something similar where we just turn these roles around. All right, we're going to add, instead of having the acid down here, we're going to have the base down here, and we're going to add acid to it. All right, and what you're going to have is essentially the opposite. All right, you can notice here that these two curves are mirror images of each other, and you're going to have an equivalence point that would be at 7. All right, so moving on. All right, I've gone ahead and drawn in an extra one right here, adding a strong base to a weak acid. All right, what are some things that are going to be different? All right, well, if you're starting with your bottom solution here, if you're adding something to a weak acid, then this starting solution down here would be a weak acid. And so we would not expect that its pH would be quite as low as if it were a strong acid. So that's why its pH starts lower. All right. So if we're adding a strong base to it, we know that if we add enough of this stuff right here, eventually would have the pH of that strong base, so it's going to end with a high pH. All right, so we're going to get this graph right here, and it's going to have that that equivalence point. All right, which is the same as it's going to be its inflection point. All right, but the thing is that equivalence point is not going to have a pH of 7. All right, so in this situation, you would expect that equivalence point to be greater than 7. All right, the adding a weak acid to a strong base. All right, strong base would be here, and it would be essentially the mirror image of this guy right here. All right, so adding a strong acid to a weak base. Again, if we're starting with a weak base, its pH is not going to be quite as strong as if it's a strong base. All right, its equivalence point is going to be less than 7. And again, we could turn the situation around and it would be the mirror opposite. All right. Okay, so in this next part, I want to talk about this type of chemical that's often used in pH titrations, which is a pH indicator. All right, so to introduce this, I want to go back to this first situation right here. All right, we want to find out something about this solution based on how much of this, what we consider the standard solution. So the solution that you're adding in the burette is what's considered the standard solution. All right, so we want to know how much of this we have to add in order to get to that equivalence point. All right. Well, here's the thing: when we're adding this material, let's say that this is sodium hydroxide solution, and this is hydrochloric acid. All right, you're adding this would be a clear colorless solution. This would be a clear colorless solution, and remember that the product is just salt water. All right, which is going to be clear and colorless. All right. So when we're doing this titration, unless we have a pH meter down in there, all right, how would we know once we've gotten to this point? All right, because if everything is just clear the whole way through, we wouldn't have any way of saying, hey, this thing, I'm now completely neutralized. All right. Of course, if we're monitoring it with a pH meter, we would, but when you're doing this in a lab, a lot of times it's good to have a way of telling when we've gotten to that point without having to use a pH meter. All right. That's where the role of pH indicators come in. They offer a visual indication of when the neutralization is done. All right, so let's talk a little bit about how they work. All right, so essentially all a pH indicator is it's a compound that it is essentially a weak acid. All right, and since it's a weak acid, it can either exist in its protonated form, what we consider its acid form, but at certain pHs, it's going to exist in its conjugate base form, its A- form. All right, and what makes something a good pH indicator is if these two things have distinctively different colors. All right, so if the acid form of it has, we'll just say color 1, all right, and the A- form has color 2, and they're very different. Say like a blue and a red. All right, something that you can't help but to be able to tell the difference between. All right, you could use it as a pH indicator. All right, and the way this works goes back to something we talked about in a recent video. All right, and that thing is that when we were talking about how the pH of a solution affects the relative amounts of the acid and the conjugate base whenever you have a weak acid. All right, so remember that in this example right here, if we were to add, because of this acid dissociation reaction right here, if we were to add some strong acid, right, we would essentially be adding some H3O plus, and this is a reversible reaction that would force this reaction this way. So at high pHs, you would expect to have lots of the HA form. All right, at low pHs, you would expect to have the A- form, and we discussed this in the video a few videos back. So that's the same situation you're going to have with a pH indicator. It's just a special type of weak acid. All right, and all you're going to do when you're doing this is you're just going to add a tiny amount, just a smidge to your reaction. So when you're doing your acid-base neutralization, you'll just add essentially just a pinch to here, and it's going to be enough. These things are designed so that they have very vibrant colors. All right. So if in that original solution the pH is very low, all right, that would mean it's very acidic. In that situation, if you've got a low pH, that would mean you'd have lots of H3O+. Le Chatelier's principle says it pushes it this way. We're going to have way more of this and not very much of this. All right, so that means that the color would be that of color, it would be color 1. All right, but what happens as we do our pH, our titration, we're going to start adding some base to that, and that's going to start to change the pH of this solution down here. All right, and eventually, so remember, adding base is the same thing, adding hydroxide is the same thing as taking away H3O+, because there's that relationship between those. So as the pH increases, you're going to start to see more of this type right here exist and less of this. All right, so at the high pHs, you're going to have more of this and less of that. So therefore, the color of the solution would be color 2. All right, so the best thing that you can do, or what you want to do when you're doing using a pH indicator, is you want to choose a pH indicator whose pKa is very close to the equivalence point of your reaction. All right, so a list of common pH indicators are listed in Table 22 of the data booklet. All right, and a lot of these pH indicators have very common sounding names: methyl orange, bromophenol blue. All right, so the chemical sounding part of it tells you something about the structure, the chemical structure of it. The color tells you something about the color, the approximate color that you're going to see. And the names have just kind of stuck through time. All right, but you can see here that these different, essentially each of these is going to be a weak acid. All right, it's going to have an acid form, but it's also going to have a conjugate base form. And its acid form is going to have one color, and its basic form is going to have a distinctly different color. All right, so notice one thing about this: the pKa of the weak acid, which is your pH indicator, is right smack dab in the middle of the range that it would be effective at determining. All right, so essentially what this means is that at pHs that are say 3.1 and below, it would be red. You would expect to definitely have a red color there. Actually, pH is starting to get below 3.7. It's going to be more reddish. All right, in pHs that are above 3.7, it's going to start to get more yellowish. All right, so below 3.1, it's going to be completely red. All right, above 4.4, it's going to be completely yellow. And if you're in between, it's going to be a transitioning color. All right, but remember one thing about these pH titrations is that there's generally not a gradual transition when you're close to the equivalence point. So even though it might seem like it's a wide range of pHs that it changes color over, remember when you're doing these titrations, take a look right here. In that little bit of the graph right there, we've only added a very small volume of the base, but the pH changes drastically. All right, so what you're going to find is if you have, you're going to want to try to find a pH indicator whose pKa is very close to that equivalence point that you're interested in. And if you have that pH indicator in that solution, you will see a very distinct color change. Literally it can happen over the course of like a drop or two of your solution.